Hi everybody, thanks for coming along to my talk on teaching Scala. My name is Noel Welsh. You can find me online at those places. I just want to give a quick shout out to my employers who I put on tiny little type at the bottom here. They're so small. They are Underscore, which is a UK-based Scala consultancy. Hopefully you've heard of us before. And Inner Product, who you almost certainly haven't heard of because it's a very new company. That's basically doing what Underscore does, but over in the US. All right, but you're not here to hear about me. So what are we here to hear about? We're here to hear about teaching Scala. So let's get a little outline of what I'm going to talk about and a bit of context. So I've been teaching Scala for about 8 years, roughly. And I've learned a lot in that. I think I'm a much better teacher now than I was when I started, and I think paradoxically, I think I'm a much worse teacher than when I started. So what I've learned is that teaching is definitely a skill. We've all had some experience with teaching, like we've all been taught at some point in our life. So if you were to go and do some teaching, you'll probably have a better baseline than, say, if you pull someone off the street and say, do some coding, because most people don't have any experience with coding. But it doesn't mean that even though the floor is high, it doesn't mean the ceiling is lower. So I've learned that there's quite a lot you can do to improve teaching. And I think teaching is something that we undervalue in our programming communities. I think teaching is a really valuable skill, and I'm going to give you 3 reasons why I believe that. So firstly, if you are a senior developer, then it's probably part of your job description to teach, mentor junior developers, make them more productive. Who here thinks that's part of their work, out of interest? Anyone going to admit to it? A few hands going up, okay. Cool, so if you can get the junior developers more productive faster, that means more work gets done, less hassles for you, maybe you get back to programming. Senior developers never get to program. So I think it's something that if you can improve at teaching, then you can get a lot of rewards from that. Something I'm personally involved with is in ScalaBridge. Anyone heard of ScalaBridge before? A few hands going up, cool. Okay, so at ScalaBridge we try to increase the diversity in the Scala community by bringing new people in, people who don't necessarily have any programming background, sometimes actually quite experienced developers. And we're trying to teach them Scala, so it's a place where we get to use those skills for what I think is a good cause. And finally, we teach ourselves. So I have discovered that there's not really a very strong demarcation between teaching and learning. In fact, teaching is a great way to learn something. And so knowledge of teaching can help us in our own learning. That's something you have to do in this career is learn new stuff all the time, whether that's like new Scala libraries and new technologies like, I don't know, React or Idris or Rust or something. And so knowing how to teach is actually very useful when it comes to learning new things yourself. All right, so that's my justification for why teaching is interesting and you should listen to this. What am I going to talk about? I'm going to give you 5 tips for teaching. I could probably talk for a very long time about teaching, but I'm going to try to keep it in 40 minutes or so. So 5 tips, things that you can apply immediately to what you're doing. If you're doing teaching in individual context, in a group context, different things you can do. And then I'm going to give you 5 further resources where you can go to learn more if this stuff interests you. I obviously can't cover everything in the time we've got. So that's the main things I want to talk about. Give you some ideas of how you can improve teaching in whatever context you do it, and then point in the direction to find out more. Before we get into that though, I want to talk about just a bit of overall context of way of thinking about what I'm discussing. So learning to code is a thing. Everybody's talking about learning to code, and you go onto your favorite internet forum and there'll probably be some discussion there at some point in time if your internet forum is vaguely technically related. And people will talk about language choice, and that is basically where the conversation will stop. It will be, should I use Python or JavaScript, or should we use QBasic, because that is what I learned on. I didn't actually learn a QBasic. I learned kind of maybe on VIC-20 basic, shows you how old I am, but probably really Turbo Pascal was where I really started doing a bit of programming. So you get these kind of discussions, arguing over the language choice. And to me, that's not a very interesting discussion. All those languages I previously mentioned, I think, are not particularly great for teaching. Is Scala a great teaching language? Well, it's an okay one. It certainly could be worse choices. It's probably not the best language either, but I'd say any kind of functional programming language is a good choice, and I'm going to show you some reasons later why functional programming is good for teaching, in my opinion. But that's not really the focus of what I want to talk about. There's plenty of interesting discussion there. What I do want to talk about are things that people don't usually discuss, and the first one of there is the curriculum. So the curriculum is, what are you actually teaching? Saying you're teaching Python or JavaScript or Scala, there are many different ways you can do that. So I'm going to talk about the curriculum and give you some ideas of things that we teach in our professional training and at ScalaBridge and so on that maybe you haven't thought about teaching before. And then the other thing I want to talk about is pedagogy. So curriculum is what, and pedagogy is how. And here there are lots of different techniques that you can use, and I found they make a real difference in my teaching. So again, something that people don't often discuss, pedagogy. All right, anybody have any questions at this point? No, okay, cool. Well, let's get into it then. So 5 tips for teaching. What have we got? Tip number 1 is teaching notional machines. What is a notional machine? Anyone have a notion of what a notional machine may be? So what we can think of a notional machine is basically like a machine model, so that people can understand how programs actually work rather than cargo copying stuff out of Stack Overflow and doing random walk in the space of programs until something works. It's sometimes called a genetic programming. It's a bit of a jab, that's an AI background. So if people actually can understand how programs work, they need to have some kind of model, and that is what we mean by a notional machine. So it's a simplified machine model. When you think of a machine model, you may think of like CPU with registers and a stack and a program counter and like memory. And yeah, that is a sort of notional machine, but you don't need something so complicated for functional programming. What you need is something really simple, and that really simple thing is called substitution. And you may not have heard of the term substitution before, but you almost certainly know what it is because you were taught this in primary school. So who has heard of the term substitution before? I have. Okay, about half of you, that's cool. That's good to know. So let's go through substitution and we'll see who managed to get through primary school. So let's say I have the following program. And the substitution rule is, whenever you have a name bound to a value, wherever you see like a use of that name, you can substitute in the value the name is bound to. So here we have A bound to the value 1, and so when we have uses of A, we can substitute in 1. Get that. Who can tell me what this complicated expression evaluates to? Anyone? Yeah, just shout it out. Sorry? Not the whole thing, just this one here. What's B? Okay. Who passed primary school here? Anyone?
7.
7, okay. That's one suggestion. Anyone, any other suggestions? What 1 plus 1 is? 2, okay, awesome. You passed primary school, good. Whenever I ask these kind of questions, there's always deathly silence. Everyone thinks it's a trick, but it's not. All right? It is indeed 2. Well done. People said 2. Bad luck for 7. It's a good try, though.
We have a different circular performance.
Right, yeah. It was like a base 8 or something, or I don't know. Okay, and we can carry on. Now we know that B is bound to 2. We can get B, uses of B, and we can substitute in 2 and get 2 times 2, which is?
4.
Yeah, exactly. Okay, and so that is our very simple, very straightforward, very primary school notional machine using substitution. And that works. Beyond these simple examples, it works for methods. You maybe sometimes need to do a little bit of work about renaming and aliasing, but substitution works in a very straightforward way for methods as well. It works for types. You can substitute in types anywhere, and that is a reasoning technique which I'm going to show you a little bit later. Very powerful thing to do. And in fact, it works for all pure code or referentially transparent code or functional code or whatever you want to call it. You can just use substitution to reason about it. At this point, you might be thinking, you know, this is really basic, easy stuff. I learned this in primary school. What's the big deal? And that is exactly the point. The point is, it is really simple, really easy. You don't need to worry about registers and stacks and program counters or whatever other nonsense. It's just primary school level stuff. That is the whole point. That is why we like immutability in functional programming. We don't like immutability for its own sake. That would be dogma. We're not dogmatic, well, sometimes. But we like immutability because it allows us to reason about code using substitution. we like monads for the same reason. They allow us to reason about effects up until the point when the monad is run. You can reason about maybe using substitution. And in fact, I think this idea of reasoning about programs using substitution is one of the principal points of functional programming. One of the real core ideas here, that using composable local reasoning, if you like, with lots of fancy words that all basically mean using substitution. So it's a really big thing, and it's a really simple thing as well. So very powerful, good thing to introduce to programmers. Okay, so that's substitution. Let's move on to number two. Number two is programming strategies. And what I mean by programming strategies are systematic, repeatable ways of writing code. So if you can write code in a repeatable way, that means all your code is going to look the same. Everyone can use the same techniques. You're never going to be reading Bob's code and going, what the hell is this doing? Because it's all going to be using the same kind of techniques that you know. So I think that's another very powerful thing. This is similar to design patterns from the OO world, but these are wider in scope. I'm going to give you some examples in a moment. I think that compared to design patterns, these strategies are both more formulaic, more systematic, and they cover more code, more cases, shall I say, than design patterns did. So these programming strategies are something that I think are reasonably unique to how we at Underscore and in product teach programming. We've identified 10 of them. I'm going to illustrate 3 of them. These 3 are like the main ones I think we could use all the time. And they are algebraic data types, structural recursion, and following the types. So just out of interest, who has heard of any of these terms before? I have. I've got the slides. That's good. Okay, cool. Most, keep your hand up if you've heard of structural recursion before. I'm just curious. Okay. So I thought most people have probably heard about algebraic data types, but maybe not the other two. You'll probably recognize them once I describe them. Probably just giving names to stuff you know already. So algebraic data types, lots of hands go up. Anyone to tell me what algebraic data type is? I will tell you because this will get painful. Basically, whenever you can define data in terms of a logical and or a logical or, you have something that is an algebraic data type. So an example, if you wanted to define Apple's range of fine machines, you could say, well, a Mac is a MacBook Pro, or a MacBook Air, or a Mac Mini, or an iMac, or maybe even a Mac Pro. Who knows if they still make those things anymore? They're rumored to come out later this year. We'll find out. So that's an example of like a logical or. Then if you're looking for like a logical and, you could say, well, a MacBook Pro itself is specification of what size do you want, 13 or 15 inch, I think these days, CPU, the RAM size, the hard disk size, all these different things. So it's like CPU and RAM and hard disk and size and so on. So that's an example of like a logical and. You find them in your own settings where you have like a customer, maybe a preferred customer or a normal customer, like somebody signed up for your loyalty program, or like a user could be an admin or a normal user, and there could be different types of admins. And then the users themselves will probably have like a password and a login name and maybe like a first name they use, display, and this kind of stuff. So that's where you're getting these logical ors and logical ands. So we can boil this down to like these two things, and an or, and if you say if A has a B and C, then you should write the following code. Define a case class, A, and it has a B and a C. This is how you tell Scala. Hey Scala, A has a B and C. And then if you have an or, like that, well then you write the following code. And so whenever you see this, you know, it's just a verbose way of saying A is a B or C, and you're also forming the compiler of this structure in your code, so it can then do things like exhaustivity checking and so on. So this is just, you should write this code directly whenever you've got that structure worked out. So let's have an example. So implement the simply linked list, standard kind of list in Scala. We say a list is pair or empty, and we can go bang, immediately write down that code, which is just taking the pattern and substituting in list, pair, and empty for A, B, and C. And then we can go like pair has a head and a tail, and we just go and fill those in, haven't given them types yet. Say the head is of type A, and tail is of type list A, and then we can just go and fill in our types. And we are done at this point. Some of the more experienced developers might be raising your eyes, and I'm saying this is an invariant one, just because the code is a little bit shorter and a little bit more approachable if there are any beginners here. Yes, you can write it in a covariant way if you want. If you don't know what I mean by invariance and covariance, don't worry about it, it's irrelevant for this discussion. I'm just, if you're sort of wondering what's about covariant, I'll explain why, keeping the example simple. Okay, so that's the whole thing. Once we have that structure of the data, the code just followed in a fully automatic way. There's no need to think about the code. It follows directly from getting the data description down. On to our next programming strategy, structural recursion. So if the rule for algebraic data types is that if you can describe the data in terms of ands and ors, and you use the algebraic data type rules, the rule for structural recursion is whenever you're doing any kind of transformation on an algebraic data type, you can implement it using structural recursion. So you've got to think, am I trying to do something on algebraic data type? If the answer is yes, I can reach for structural recursion. You don't have to use structural recursion. There might be a method that does what you want, like filter or find or map on a list, say, but you can implement anything you want using structural recursion, right? The two ways of implementing it in Scala, pattern matching or polymorphism, both valid. They have advantages and disadvantages. I'm going to show you pattern matching because it's a little bit more compact and maybe a little bit more familiar. I don't know. So let's see. The rule is if A is a B or a C, then you write this type of pattern matching. Case have an A, you have to have the case for B and the case for C. What are you going to do? Just following the structure of the data. And when you have the AND case, A has B and C, then you need to pull out that B and C and you can use them on the right-hand side. There's one additional rule, which is that when the data is recursive, the method itself is recursive. And this is really handy for beginners because they often struggle with recursion. They try to evaluate it all in their head, and then they get a little Stack Overflow in their head, and it's not pretty to watch. The great thing about recursion, structural recursion, is you don't have to think about the recursion. The rule tells you when you put the recursion in, and it says if you get the individual cases correct, then the whole recursion is guaranteed to be correct. You don't even ever need to think about the actual recursion. So let me give you an example. If we go back to our list, we see that list is recursive. The tail of a list is itself a list, so the data is recursive. So if we're defining some kind of method of a list, do something, and here we have our little pattern match. We said, a list is empty or paired, so that's what the structure is. The pairs, head and tail, you pull them out. We also have on the right-hand side, we get a recursion in here. We know that there's going to be a recursion in there, but I've got these question marks to say this is not the complete answer, but we know it's going to be part of the answer. And once we've got that, we don't need to think about this recursion anymore. It's guaranteed to be correct, as long as we get the little question mark bits correct. Okay, so that brings us to the question of how do we complete the right-hand side. So we've got the left-hand side completely just from the structural recursion pattern. The right-hand side, we've got this filled in, but we need to get these little bits sorted out. So how do we do this? And that gets me to my final programming strategy here, which is following the types. Probably something you do already, by giving a name to it and making it a little bit more structured, helps beginners, helps in teaching. So the basic idea is letting the types guide you. Just like Luke was guided by the force, here we will be guided by the types. Programming with the eyes closed might work. Programming without the computer is probably not going to work too well for you though. So there's some differences from using the force here. I'm referring to obviously the tapping the desk stuff for people who are struggling to follow along. So the way that we follow the types is we need to do the following things. We need to work out what is the goal, what is the type of the result we're trying to get. What do we have available, what functions, methods, data are available in scope that we can use, and then it becomes like a little jigsaw puzzle. How can we assemble the things that we have available so that we reach our goal, working on the type level? And there we go. So let's see an example. Let's say we are implementing map on list. We have this method header. This is given to us because map always has the same signature. Right, so we know we've got that, but we need to fill in the actual implementation. Well, the first thing is that we're transforming an algebraic data type, so of course we can use what strategy is it? Yeah, that's great. That's the better answer than I get from most of my classes. So that's cool. Structural recursion. So we can just fill out this, get that straight away. What are we missing here? Slightly trickier question. So what was that? Recursion, exactly, yes. We need the rule for recursion, it gives us on the right-hand side. So we've got this called a map here, and I just put question marks in for the parameter. We can figure it out using this following the types method, though it's probably pretty obvious to you what that parameter should be. Okay, cool. So then we go. Follow the types. Let's look at the empty case first. What's the goal? Well, the goals are written right there in our code. Produce a list of B. Okay, so type it down. What have we got available? Well, we've got F of type A to B, so let's note that. We've always got the constructors as well. People often forget the constructors when they're first learning. And they are empty, goes to list of A, and A is any type, and we like, and of course pair. Okay. At this point, say the only thing we can do is use empty. We can't use pair because we don't have anything to apply. That's not a value of type A. We can't use F because we don't have anything to type A. This is all we can do, write empty. There is no other possible implementation. So the types constrain us to be correct. They force the correct implementation upon us. We write it down. Let's get pair. Okay, same thing. The goal is as before. List B. What's available? We've got F as before. We've got the constructors. And now we also have in scope the head, tail, and the recursion. And so let's add those to our list. H type A, tail list, and the recursion, which is going to give us a result of list B, because that's specified by the types. All right, now we get to do a little bit of jigsaw work, a bit of following the types. We're going to get to this solution pretty quickly here, but maybe just spend a little second looking at it, figuring out how to do it. I'm sure you can do it yourself. First thing we can do is say, look, I got a head of type A, I've got a function from A to B. B seems like it's getting me closer to a list of B, so why don't I just apply F to the head and put that in there. I got something of type B. And then I can go, well, I can take this, I can take pair, and I can take this recursion, and they will construct for me a list of type B, give me the answer. So that's what I'm looking for. There are actually a few other answers you could go here. You could have said we can do empty as before. We could just do the recursion, list of B, or we can do the correct answer. So there's three possibilities here. Let's pick the type signature, only one of which is correct. But at least we can use the types to narrow down the possibilities and then select the correct one from the options that we have. All right, so we got that. Now, final thing is to work out what this parameter should be, and this is fairly straightforward. The goal is something of A to B. There's only one thing in scope, that is F, so F it is, and we're done. So, at this point, oops, wrong slide, we have implemented this using almost entirely mechanical processes. We had to do a tiny bit of thinking here to choose the right solution, and that was it. The rest of this all just follows from the structure of the data. Okay, so that's a really great thing if you're like a beginning programmer. There's a whole heap less confusion you can have, a whole heap more correct code you can write more quickly. And in fact, it's a great thing if you're an experienced programmer because you can do the same thing. I do this all the time. I work out the types I want, and then I just blindly keyboard cat, as we call it, my way to a solution. All right. So, tip number 3. We're now crossing over from curriculum into pedagogy. This tip is a mixture of both curriculum and pedagogy. It's the idea that there is more to programming than just coding. More to life. I'm not going to say anything deep and meaningful here, unfortunately, about life. I'm just going to talk about things like debugging and tool use. So there's a whole bunch of knowledge that you need to be an efficient programmer, like understanding how to use your tools effectively, understanding the compiler error messages. So like when Scala C says, found type B, switch to type A, you go, ah, and run off screaming. Who's had that error message before? I have. It's a great one, love it. It has improved a bit in recent versions of Scala. It now suggests that maybe some aliasing going on, but I remember the first time I got that, I just did not have a clue what was happening. Or perhaps you're using Git, and Git says you're in a detached head state or something along those lines. Who's seen that one? What does that mean? I'm some kind of Elizabethan ghost running around with my head under my arm. Who knows, right? So one thing you can guarantee, this is like kind of a full employment theorem of programmers. When you've got these tools that give you such kind of nonsense output, there's always going to be room for people who can understand what they actually mean. But the serious point is there's a lot of implicit knowledge in programming. And to make this explicit, we can teach people how to use the shell, how to use Git, and that kind of stuff. But that's a bit of a detour, so what we want is a way to teach this knowledge without having to necessarily explicitly spend time in it. A great way to do that is by doing live coding. Anyone done live coding before? Anyone terrified of live coding? Okay, lots of head nodding. So you're thinking, but I can't think and type. And that actually is 100% the point. That's the whole idea. You can't think and type, so you make mistakes. And then you are forced to demonstrate these mistakes and error recovery from them. So you get some kind of error message up on the screen, and then you need to fix it. And that's a teaching moment where you can do it. And it's a chance for you to demonstrate your tool use as well, how you sort of navigate around, you compile to your errors, so on, compiling the code. And here's the best thing, is when you get those brain freezes, and you say, I don't know, I can't see what the problem is, instead of feeling bad, what you do is you go, we've made a mistake here, what do you think's wrong? Hand it over to the students. And then it forces them to actually learn something rather than just sitting and watching, because they have to now engage with the code, engage with the problem, reason it out for themselves. And you get a few moments to get your brain re-engaged and work out what the actual issue is. So live coding is really good, and don't be scared of making mistakes, because making mistakes is the whole idea. And don't be scared of your brain freezing up, because it doesn't matter. In fact, it's better to get the students to do the work than it is for you to do it, because you're the expert. You can do it. They're the ones who need to learn. All right. Okay, so that is tip number 3. On to tip number 4, and that is shut up. Okay, so why do I have this tip up here? Thinking while you're listening is quite challenging. If there's something coming up that you want to think a little bit more about, I know for myself, I will then sort of zone out from whatever's been said to me whilst I follow that thread of thought. And what I've just seen in myself and in other new teachers is people are really keen to help, and as soon as you see a student struggling, or you just want to jump in there and show them the answer. And I used to do this. I used to, like as soon as I see a student, give me exercise, as soon as I saw a student, I would just rush, having problems, I'd rush in there and say, let's start doing this and this and this. Now, I want to give them a chance to actually engage with the problem. I have to thank Anna Shipman, now the FT, if anyone knows her. She was the person who said, hey, you need to give people some time. I'm like, yes, I do. So just giving people time to think is really handy. Don't feel like you have to fill all the silence with talking or helping. What you can do instead is once people have had a bit of time to think, and they seem to be going nowhere, you can start giving them prompts for thinking. Don't give them a solution, but maybe give them a prompt like, what coding strategy are you using here? And say, I don't know. And you go, okay, what are the available strategies? Algebraic data type, structural recursion, following the types, or whatever. And then you can then at least walk them through and get them to engage with the problem a little bit more. Another thing that's good to do is give feedback. Tell them, say, I think you've made a little error here. Particularly newcomers, they will have this code that gets an error and they just won't know where to start. You can maybe narrow down the problem a little bit for them, say, I think the error's in here, and just put them on the right track. That can be nice. Another thing to do is really good is to get the students to explain their reasoning, to make their mental models concrete, vocalize them, and you'll probably find a whole heap of confusion in there once you ask them to do this, and that means that you know where you should be addressing your teaching rather than just kind of jumping in and helping stuff. So you say to them, explain to me what you're doing here. This can be very interesting. You can get very, very confused responses out. That's okay. That's part of learning. You've got to build these mental models. At least if you know what they got right and what they got wrong, you know what you should be focusing on. So the teacher's job is definitely to present material. There is a school of thought called constructivism that you just like throw the tools at people and say, have fun, but the research shows it's not as effective as having a teacher. But once you've presented material, the job is not to rush in and fix all the errors. Really, what you want to do is uncover the flaws in people's models that they've learned and then help them correct that. The students have to engage with the material. They have to be the ones who do the learning. As much as you want to see them all succeed and succeed really quickly, you have to let them make those mistakes and fail and mess up so that they can learn. So yeah. don't be a hero. Don't be the oracle who's got all the truth. They have to grapple. They have to fail. All right. Now on to point 5, which is again a pedagogical idea. This is this concept called peer learning. This idea here is that the students can teach each other, and that's a great way to learn. So teaching, I think one of the best ways of learning is actually teaching, because teaching forces you to structure your knowledge in a way that you can convey to other people. And I've known my own Scala become a lot better from the teaching I've done. I'm much more systematic in the way I code. I have much more high-level view of what I'm doing, much less sort of in the code directly. The code itself is, in some ways, just an expression of the design, as I showed with those programming strategies. So yeah, teaching, really good thing. It forces you to make this coherent mental model. As soon as you try to explain something to someone else and you don't have a coherent model, those errors in your model become obvious. So how can we do this? I'm going to talk about 3 ways that we can get students to teach each other. The first way is what I call the hypothesis game. You ask a question and you ask the students to form a hypothesis and answer. And initially, they don't share their answer. You want them to just think of the answer, what they think the solution is, and then they've got to turn to another student and tell them the answer and critically justify it. Why do you think this is? Make them formalize that mental model, make them vocalize it. Is it coherent? And we'll find out pretty soon. In some setups, you'll see, if you go and read the literature, people do these multiple choice questions and then people vote for different answers, and you can see like sort of before and after they discuss it, how their votes change. We don't do that, we don't have the sort of setup for that. But I think the critical thing is really this bit here, it's justifying your answer. So you don't need to do this kind of voting stuff. That's the critical thing. Okay, so that's very effective. Another thing is pair programming. Who does pair programming at work? Anyone? Cool, lots of people. Okay, more than I expected. So that could be 2 students, 1 keyboard, or it can be many students, 1 keyboard. Mob programming, as it's sometimes called. Anybody experienced with mob programming? Okay, cool. And there are a few suggestions here. Number 1 is don't let anyone bogart the keyboard. I'm bogarting the mic right now, so don't let one person just do all the typing. The person who's doing the typing is sometimes not doing so much thinking, or that's kind of the ideal, is you really want the non-typist to be very active in the process. So if someone is just typing away, and everyone else is zoning out, it's not effective. You've got to make sure it's effective by getting the non-typers doing things like suggesting strategies they can use, think about the high-level stuff, probably not so much focusing on the kind of minutiae of the spelling errors and so on. There is a very nice guide to pair programming, pair programming guide. Go read that, but it seems like a lot of you have experience with pair programming anyway, so you probably know how important it is to keep everyone active in the process. Third technique is the rubber duck. And this is something you can do when you're on your own, if you're just, if the teacher is you and the learner, the student is also you, then just explain to some sort of inanimate object. This could be like the sort of proverbial rubber duck, it could be a cat if you have a cat. My cat is inanimate most of the day, apart from when it's hungry. Anything that's not going to really give you grief, so maybe not your partner, probably doesn't want to hear you yammer on about programming. And again, it's the same benefit of all of these ideas. You're forced to vocalize, forced to formalize your mental model, forced to discuss your assumptions, your hypotheses, and so on. And as soon as you do that, things become a lot clearer. I do this, and I guess it's the same thing like whenever you ask for help, or whenever you write an email, go onto chat or whatever, and say, can anyone help this problem, blah, 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 suddenly you realize the answer. So yeah, just forcing yourself to think about your thinking, kind of metacognitive stuff, really works well. So yeah, that's basically pair programming when you're alone. All right. Okay, so those are my 5 tips. I now want to give you 5 further resources where you can go and find out more about teaching. As you can imagine, it's a massive field, right? Education field. It's computer science education, it's a fairly big field, but education itself is enormous. So here, just to kind of dip in a few things. So the first thing is this journal article, 10 quick tips for teaching programming. So I gave you 5 tips, they're pretty quick. It's got 10 tips in it, so it's like double the value of my talk. It is a very easy to read article. It's very pragmatic, it's very focused on things you can do. One suggestion I would say is if you do go and read it, think about the underlying cause. Why do the techniques they talk about work? What is going on there? So like they have pair programming, for example. There's no magic in pair programming itself. The magic is in making people communicate, stay active, and this kind of localizing them into model stuff. Another book, so a book by one of the authors in that previous paper, it's called Teach Together, you can get it online. Really nice book, very short, very to the point, but covers more than, say, the paper does, gives you a little bit more theoretical understanding. It covers just about everything, I would say, apart from the programming strategies, which, as I said, are something that are moderately unique to what we do. If you're interested in where the programming strategies came from, then there's this book, How to Design Programs, and they have what they call design recipes, which are the jumping off point where we developed our programming strategies from. And that's probably the best place to find that sort of stuff at the moment. So these are all computer science education resources, just moving out into the bigger field of education itself. There is a site called visibleLearning.org, and what this does is collects the work of a guy called John Hattie, who's done his enormous meta-analyses of education studies. So he's got thousands of studies, and he's sort of tried to work out what's the most effective techniques and what are least effective and rank them all. I don't think his actual calculations are all that accurate, but they don't really need to be. What is useful for me is a rough kind of ranking of what's effective and what's ineffective, and also just names that I can then go and put the search for. So I found a lot of things from here, sort of the idea of peer learning, something I got from there, I think micro-teaching, metacognitive strategies, which are programming strategies are an example of. So if you really want to dive into literature, it's a good way to sort of focus your search, because that's what I found it to be. And finally, your own practice as a teacher. But I wouldn't say just your own practice, but your own deliberate practice and reflection. So to be a good teacher, you need to be a good learner. You need to learn from your own practice and do everything you'd expect and hope a student would do. So look at your teaching. What went well? What did not go well? How can you improve it? So an example, a couple of weeks ago I was over in Silicon Valley with a company I probably shouldn't name, but let's just say they design computers in California. And from the teaching I did there, I felt that I didn't do such a good job on assisting people when they were struggling with the exercises, and my reflections were a lot of the points that I presented and the shut up tip came from. So if you are reflective on your practice, you'll learn a lot more. It's very useful to have a bit of theory to hang that reflection off, but you can just learn a lot from what you do. It's kind of depressing in a way because you don't think you're so good, but that's kind of the paradox of expertise. All right, so there are 5 further tips. So, conclusions. Firstly, teaching is a skill. It's a skill that's got quite a high ceiling. I think I'm just being sort of climb up there. And it's definitely a skill you can learn, and it's something that's not very different from learning. So I think it's a very useful thing to get better at, because I believe that learning is something we need to do in our careers, and teaching is something that is very useful to do, either for yourself or for your colleagues. Very handy thing to have. Going over my tips again. My 5 tips were the notional machine, the programming strategies, recognizing there's more than coding. If you want to see how much more there is, if you get someone who's never programmed before and try to get them programming, my goodness, it is a revelation of how much knowledge you've implicitly accumulated. So I've been trying to teach my son to program a little bit recently. He's 10 years old now, very keen to get going, and just things like putting the syntax in the right place, putting the delimiters around strings, or putting the curly braces in. It's this kind of stuff he forgets, and how you use the tools, and wow, so much going on there. My 4th tip is to shut up, something I'm very bad at. And my 5th tip, peer learning, getting people to teach each other. Now, if you are keen to teach, and I hope you are, let me talk a little bit about ScalaBridge. So ScalaBridge, as I mentioned at the beginning, is this diversity-focused movement. We're running ScalaBridge in London starting May 21st. We're running for 12 weeks. It's going to be 6 sessions over 12 weeks. We've got 50 people signed up and another 50-ish, another 20-ish on the kind of waiting list who'd love to get in. And we need more mentors, more people to help these students get better at Scala. They range from like never programmed before to quite experienced programmers. It's a lot of fun. I've done it before in different contexts. I really enjoy it. Come along, be a mentor. That's the website to get in on, scalabridgelondon.org. You'll find a sign-up form for mentors there. You will enjoy it. So, that's all I've got to say. That's my contact details again. You've been awesome. I've been just about on time.